Welcome students. Today we will study interference of light. In the last chapter we have studied certain properties of light such as reflection, refraction, polarization, etc. Similarly, one of the important properties of light is interference. It can be explained on the basis of superposition principle. Any number of waves can pass through the same part of the medium without affecting any of the characteristics of the other waves. Hence, the resultant displacement of a particle in that part of the medium can be obtained by using the principle of superposition. When two waves arrive at a point in a medium simultaneously, each wave produces its own displacement in the particle at that point independently. The resultant displacement of that particle is the vector sum of the displacements produced by the waves. As light is composed of waves, when two light waves arrive at a point in a medium simultaneously, superposition takes place. If crest of one wave matches or coincides with the crest of the other, or trough coincides with the trough, the resultant displacement of the particle is maximum upwards or downwards. As the intensity of light is directly proportional to the square of the amplitude, at the point of maximum displacement, we get maximum brightness of light. Such points are called bright points. On the other hand, if crest of one wave coincides with trough or vice versa, the resultant displacement of the particle becomes zero, or the particle doesn't move at all from its mean position. Hence, intensity of light at such point is zero. Such points are called dark points. Thus, the phenomenon of alternate enhancement and cancellation of the displacements produced by superposition of two light waves is called interference of light. Thus, due to interference of light, we get alternate bright and dark bands. This pattern is called interference pattern of light. If this pattern is steady or remains unaltered with respect to time, it is called steady interference pattern. There are 5 important conditions to obtain the steady interference pattern. These are: the two sources should be coherent. The second condition is the sources should be monochromatic. The third condition is the sources should be of same intensity. The fourth condition is the sources should be narrow or linear. Distance between the sources should be as small as possible. The two sources should be coherent. Two light sources are said to be coherent if they produce light waves with zero phase shift or a constant phase difference. If this condition is not satisfied, the position of bright and dark points will change at a rapid rate of order of 10 raised to 9 per second, and we cannot distinguish the bands. Practically, it is impossible to obtain coherent sources from two separate sources. To overcome this difficulty, two images acting as the secondary sources of light are derived from one and the same source of light. Now, any change in any one of the characteristics, such as frequency, amplitude or phase, will be same for both the secondary sources, so the images act as ideal coherent sources. The second condition is the sources should be monochromatic. Mono means one, chroma means color. That means the sources should emit light waves of same frequency or wavelength. It is essential for a steady, well-defined and regular interference pattern. If this condition is not satisfied, a multicolored pattern can be obtained. As color of light is decided by wavelength of the wave, it can be said that the sources should emit light of equal wavelength. The third condition is the sources should be of same intensity. As the intensity of light is proportional to the square of the amplitude, it can be said that the amplitude of light waves should be same. When the amplitudes are exactly equal, the crest coincides with trough and the resultant displacement becomes zero, and we get a true dark point. If this condition is not satisfied, and if there is some difference between the amplitudes, the resultant amplitude when crest coincides with trough becomes slightly positive or negative. Thus, the intensity at such points cannot become zero. Hence, instead of getting true dark point, we get less bright point. Thus, the interference bands cannot be distinguished properly. Hence, for distinct pattern, the intensity of light should be same. The fourth condition is the sources should be narrow or linear. An extended source can be considered to be made up of number of point sources. Each source emits its own wave trains which interfere with the wave trains of the other source. Hence, the interference pattern cannot remain steady. Distance between the sources should be as small as possible. Distance between the adjacent bright and dark bands is called fringe width, is inversely proportional to the distance between the sources. Hence, as the distance between the sources increases, distance between the bands decreases and the bands become indistinguishable. The conditions of path difference and phase difference to get bright and dark points can be obtained like this. For bright points, crests or troughs of one wave should coincide with the crests or troughs of the other wave. This happens only when the phase difference between the waves is either 0, 2 pi, 4 pi, 6 pi, etc. For a phase difference of 2 pi, there is a path difference of one wavelength lambda. Thus, for bright points, the path difference between the two waves should be lambda, 2 lambda, 3 lambda, 4 lambda, etc. In general, for bright points, the path difference is n lambda, where n is 1, 2, 3, 4, etc. Thus, for bright points, the phase difference between the two waves should be even multiple of pi, or the path difference should be integral multiple of wavelength. For dark points, crest and trough of one wave should coincide with troughs and crests of the other wave. This happens only when the phase difference between the waves is pi, 3 pi, 5 pi, etc. or the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, etc. In general, for dark points, path difference is n plus half into pi, where n is 0, 1, 2, 3, etc. or path difference is n minus half into lambda, where n is 1, 2, 3, 4, etc. Thus, for dark points, the path difference between the two waves should be odd multiple of pi or odd multiple of half wavelength. If x is the distance of the point under consideration from the center of the interference pattern, if small d is the distance between the two sources and capital D is the distance between the sources and the screen, the path difference is xd upon d. For bright points, this path difference should be n lambda. Thus, for bright points, xd upon d is equal to n lambda, where n is 0, 1, 2, 3, 4, etc. For dark points, this path difference should be n minus half into lambda, that is odd multiple of half wavelength. Thus, for dark points, xd upon d is equal to n minus half into lambda, where n is 1, 2, 3, 4, etc. The fringe width is the distance between two successive bright or dark bands. It can be obtained by calculating the distance between n and n plus 1th bright band or m plus 1th dark band. If x is the bandwidth or the fringe width, its formula is x is equal to lambda d by d. From the formula for fringe width, we get lambda is equal to xd upon d. Thus, if distance small d, capital D, and fringe width x are measured, we can calculate the wavelength of the monochromatic light used in the experiment. In Young's experiment and in Fresnel's biprism experiment, we measure the fringe width, the distance between the sources and the screen, and the distance between the sources, and from that we can calculate the wavelength of the light used. Similar property or similar phenomenon can be observed in light, which is called diffraction. Let us study diffraction due to a single slit. Bending of waves around sharp edges of an obstacle is called diffraction. When light wave is incident on the sharp edge of an obstacle, some part of it deviates from its straight line path and bends around the edge. When light passes through a narrow slit whose width is comparable to the wavelength of the light, diffraction takes place, and instead of only one bright band at the center, we get a series of alternate bright and dark bands on the either side of the central bright band. These secondary bands lie in the geometrical shadow of the slit. Such a pattern is called diffraction pattern. The diffraction is broadly classified into two types. Fresnel's diffraction. In this type of diffraction, distance between the source and the screen is finite. As the obstacle is closer to the source, the wavefront incident on it is not plane but it is spherical. The other one is called Fraunhofer's diffraction. In Fraunhofer's diffraction, the distance between the source and the screen is infinite. As the distance between the source and the obstacle is also infinite, the wavefront incident on the obstacle is plane. A biconvex lens is kept between the obstacle and the screen so that the diffraction pattern is observed on the screen in the focal plane of the lens. The figure shows a monochromatic parallel beam of light, that is plane wavefront of wavelength lambda, falling on a narrow slit of width A. A powerful biconvex lens is kept in front of the slit as shown. A screen is kept in the focal plane of the lens. Let O be the center of the slit, PO be the center of the screen. PO receives light waves traveling equal path lengths. So the phase difference between them is 0 and the waves interfere constructively to produce bright fringe. As we move away from PO, the waves have some path difference between them. Consider point P. It receives waves from A and B with some path difference. If AC is perpendicular to the diffracted ray from A and B, AC represents diffracted wavefront. A ray from B has to travel an additional distance A sin theta as compared to the distance traveled by the rays from A, where theta is the angle made by AC with AB. It can be shown that as angle theta increases, the intensity changes between alternate maxima and minima as shown in the graph. Thus, the conditions for maxima and minima are like this. For minima, A sin theta is equal to n lambda, where n is 1, 2, 3, 4, etc. And for maxima, A sin theta is equal to n plus half into lambda, where n is 1, 2, 3, 4, etc. Let us study Rayleigh's criteria. When we look towards very small object, very close to each other, with unaided eye, they appear to be one. But when such objects are observed through a microscope or a telescope, they appear distinct, and we say that the images are resolved or separated. The ability of an optical instrument to form distinct images of two objects very close to each other is called resolving power. Lord Rayleigh used the diffraction principle to obtain the value of maximum resolution of the optical instrument. The objective of the microscope or a telescope acts as a circular slit and produces diffraction pattern as shown in the figure. For a point object, the diffraction pattern is a bright disk surrounded by alternate dark and bright rings of decreasing intensities. Such a pattern is called Airy's disk. In the figure, an objective is magnifying two objects O1 and O2, each producing its diffraction pattern with centers P1 and P2. According to Rayleigh, the images of 2 point objects close to each other are said to be resolved if the central maxima, also known as principal maxima, of one falls on the first minima of the other. This is called Rayleigh's criterion of resolution. Thus, first minima of P1 is coinciding with the first maxima of P2 and vice versa. So the images are resolved, means they are seen separately. Using the same principle, one can get the formula for resolving power of a telescope and microscope. The figure shows working of a telescope. Resolving power of a telescope is defined as the reciprocal of the least angle subtended at the objective by the distant point objects which are just resolved. Let lambda be the wavelength of the light from the source and capital D be the diameter of the objective of the telescope. The figure shows the diffraction pattern produced by point sources at infinite distance from the objective in its focal plane. The resolving power of telescope is given as resolving power is equal to D upon 1.22 lambda. Thus, As the diameter of the objective increases, the resolving power of the telescope increases. Now, resolving power of a microscope is the minimum distance between the two close objects so that their images are separated. Let us calculate resolving power of a microscope. The minimum distance between the two close objects so that their images are separated is called limit of resolution of a microscope. The reciprocal of limit of resolution of the microscope is its resolving power. The figure shows two objects A and B separated by distance d in front of the objective of a microscope. Let alpha be the angle subtended by the object at the objective. According to Rayleigh's criteria, when the central maxima of the first object coincides with the first minima of the second, the objects are just resolved. In this condition, distance d is given by d is equal to lambda upon 2n sin alpha. Hence, the resolving power, which is reciprocal of d, is 2n sin alpha upon lambda, where lambda is the wavelength of the light reflected by the object, n is the refractive index of the material of the objective with respect to the medium from which the incident rays are entering into the objective. 2n sin lambda is known as numerical aperture. It can be seen from the formula that as lambda decreases, the resolving power of the microscope increases.